Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 7.2 from your textbook, which introduced us into how to handle trigonometric integrals. In the first video for this section, we went through and saw how to handle sort of in general products of sines and cosines. And we were able to sort of come up with a general approach for doing that. We saw that if at least one of the exponents was odd, then we could save one factor from that particular expression, save that, convert the rest using Pythagorean identity, and then use U substitution. We saw that if we were in the situation where both the powers of sine and cosine were both even, then we were forced to use double angle identities to sort of reduce the power down to a lower power and then proceed from there. In this video, we're going to be turning our attention now to not products of sines and cosines, but products of tangents and secants. And the reason that we're able to sort of examine this in a similar way is that we're, again, going to be sort of focused on trying to come up with a U substitution. Now, when we did this in the initial part of section 7.2, we were always trying to save a sine or cosine factor because the derivative of sine is cosine and the derivative of cosine is negative sine. So if we saved one of the trigonometric functions, that would be enough to sort of be the catalyst for that substitution. When working with tangents and secants, we have a similar sort of approach, but we have to be a little bit more careful. And the reason for that is that the derivatives of tangents and secants are slightly more complicated. So before we jump into talking about these integrals, let's recall these two derivative rules. Remember that the derivative of tangent is secant squared, and the derivative of secant is secant tangent. What that means is that instead of looking to save like a single factor of secant or a single factor of tangent, like we did when we were working with sines and cosines, now we'd be interested in saving a secant squared. If we can manage to save a secant squared, then we can do u equals tangent x, and our du will be that secant squared x dx that we saved. So saving a factor of secant squared, that's a good idea. Or if we can save a factor of secant x tan x, then we can let u be equal to secant x, and the du will be that secant x tan x dx. So now we're going to be interested in either saving a secant squared or a secant x tangent x. In terms of converting, right, if we save a secant squared, then the goal is to have everything in terms of tangent. And if we save a secant, then the goal, or if we save a secant tangent, then the goal is to make sure that everything is in terms of secant. Remember, in terms of converting, you can convert between secants and tangents pretty easily, just like with sines and cosines. We have a slightly different way of doing that, though. We know that 1 plus tangent squared x is secant squared x. Or, if you want to remember it the other way, you can think about it as secant squared x minus 1 is tangent squared. So these will be sort of the identities, the Pythagorean identities that we will be using. You should notice, though, again, these conversions only work when you have squares. So, again, there will be sort of some issues with parity. We'll want to make sure that we have even exponents that we can actually convert into the other trigonometric function. All right, let's jump right in and take a look at this. So, for the first one, we're going to try to perform this integral. Tangent to the fifth x, secant squared x dx. This one should be pretty easy immediately. We can sort of see that if we substitute for tangent, well, we already have that secant squared saved there, so we should be able to do this directly. So let's go ahead and just rewrite it real quick. So we have the integral tangent to the fifth x secant squared x dx. Let's go ahead and use that same sort of trick we were doing. So underline that to show us that we're not going to mess with this at all. That's just going to be there to be sort of saved and used in the substitution. Since we're going to be saving that, that is the derivative of tangent, so we should do a substitution for tangent. So u equals tangent x. Du is going to be secant squared x dx, which is exactly what we have there. So if we go ahead and do that, we get integral u to the fifth. All right, this guy here is going to become u to the fifth power. And then, of course, all of this is used up in our substitution, so we get u to the fifth du. Then that should be a very easy just power rule, 1/6 u to the 6th plus c. And then we can just go ahead and unpack that over here. 1/6, replace the u with tangent. So tangent to the 6x plus c. There we go. There's our antiderivative for that expression there. So key thing here was that everything was in terms of tangent. We had that secant squared that was perfect for the substitution. We were all good. All right, let's take a look at another one. So we want to try to perform this indefinite integral, the integral of secant to the fourth x dx. Okay, now this secant to the fourth, we don't see any tangents in there, but it certainly would be possible to save a secant squared. So let's start by sort of grabbing a secant squared and sticking it at the back and sort of recognizing we don't want to mess with that. So we can view this as secant squared dx. And again, let's plan on saving this in hopes of doing a u equals tangent x. Now, doing u equals tangent x doesn't quite make sense yet because we don't see any tangents. But of course, this is a secant squared. So we can go ahead and do our substitution that secant squared is 1 plus tangent squared. So let's go ahead and replace that. So we get the integral 1 plus tangent squared secant squared x dx. Okay, nice and easy there. Now we can go ahead and do our u substitution. U is going to be tangent x. Du is then secant squared x dx, which is exactly what we have. That's why we saved it. Then we can go ahead, bring that over here. We get the integral 1 plus u squared du. Right, this component here just becomes 1 plus u squared, and then we have our du. Then we can go ahead and integrate. Looks like we get u plus 1/3 u cubed plus c. Then we can go ahead and put the tangent back in, and we get tangent x plus 1/3 tangent cubed x plus c. So there we go. We sort of recognized, that secant was even, so we were able to pull a secant squared out. The remaining exponent was still even. So since it was still even, we were able to use Pythagorean identity to convert it in terms of tangent, and then we were able to do our u substitution. All right, let's look at a couple more. So for this next one, we want to try to integrate secant to the 7th x tangent x dx. Notice this time, it would not be a great idea to try to save a secant squared. If we pull out a secant squared, then this would become secant to the 5th x tan x secant squared x dx. This would be good if we could do u equals tan x, but with trying to get u equals tan x, we'd have to convert this guy into tangent, which is not going to be doable because it's an odd exponent. And remember, you can only convert these in squares, right? Because that's how the Pythagorean identities work. So saving a secant squared, probably not a great idea here. Let's try to do our other approach then. Well, we have that the derivative of secant is secant tangent, so if we save a secant tangent, and if everything else is in terms of secant, we'll be able to do a u substitution. So let's try that. Let's pull out a secant tangent and sort of stick that at the end. So that would become secant to the 6th secant x tan x dx. And then the idea is, of course, we're not going to touch that because that is exactly the derivative of secant. Notice now everything else remains in terms of secant. So we can do u equals secant x. And then the du would be secant x tan x dx, which is exactly what we have there, which is why we saved it. So let's go ahead and actually do our substitution then. We would get the integral. That secant to the 6th is just going to become u to the 6th, and that entire secant x tan x dx is just going to be our du. We can go ahead and integrate and get 1/7 u to the 7th plus c. Go ahead and unpack that over here. 1/7 secant to the 7th x plus c. And there we go. We were able to go ahead and do this just directly through a u substitution. All right, let's try one last one before we go ahead and try to summarize what we're sort of seeing here. So we're going to try to perform this indefinite integral secant to the 6th tangent cubed x dx. Now, the reason I sort of want to do this one before we talk about our summary is that you can actually approach this in two different ways. One way is a little bit easier, but I want to talk a little bit about how we can actually approach it two different ways. So let's attempt sort of the initial approach we talked about, which is saving a secant squared. Notice that that's going to be doable because this is going to be even here. So one way to sort of think about this is to imagine it as a secant to the 4th tangent cubed and then a secant squared x dx with the plans on saving that secant squared. If we go down this route, we would want u to be equal to tan x. That would be good here. This would be the du, and we would be needing to convert this into tangent. Could we convert this secant to the 4th into tangent? Sure, we could think about this as secant squared and secant squared, and then convert each of those into tangent manually. Okay, a little bit messy if we went down that route, but certainly doable. Let's think about trying to do it the way we just did back in the previous example, though. So let's save a secant tangent. So if we go down a different route, just showing you guys sort of an alternate approach, we can think about this as secant to the 5th tangent squared, and then secant tangent dx. So in other words, in this case, we're saving a secant tangent factor. Now, if we're saving that, the idea is to do u equals secant x. So that means this part is all good. This will be our du, and we'll need to convert this into secant. Notice that that is a bit easier, though, because why is this a bit easier? Well, we only have to do one conversion instead of having to convert two separate pieces over here and then multiplying it out. So let's go down this route. If you go down either one, though, it's going to work. It's just this one's going to be a bit messier. So let's go ahead and replace that tangent squared. If we look back, tangent squared is, of course, equivalent to secant squared minus 1. So we can go ahead and replace that. So we will replace that with secant squared minus 1. So we get secant to the 5th, secant squared x minus 1. And then we have our secant x tan x dx here. And, of course, we're saving that. Then, if we want, we can go ahead and multiply this out before we actually do our substitution. Looks like we'd get secant to the 7th x minus secant to the 5th x. And then we have our secant x tan x dx. And that's perfect because that is the derivative of secant. So we can do u equals secant x. du is going to be that secant x tan x dx, which is why we save that. So then this converts very nicely into the integral u to the 7th minus u to the 5th, all du. Then we can go ahead and integrate directly, 1/8 u to the 8th minus 1/6 u to the 6th plus c. And then we can take that secant x and throw it back in there, and we get 1/8 secant to the 8th x minus 1/6 secant to the 6th x plus c. And there we go. There's an expression for the antiderivative there. Now, if you guys want, on your own, you can try going down this route. Take this as secant squared, convert both of those into 1 plus tangent squared times 1 plus tangent squared, multiply all that out, get everything in terms of tangent, and then do your substitution. If you do all that, it will certainly work. What you will find, though, is you will get a very different looking answer. You'll get an answer entirely in terms of tangent, whereas our answer was entirely in terms of secant. They are equivalent answers because there's conversions between the secants and tangents, but do be aware that they will look pretty different. And that is something we should mention as we're getting deeper into these techniques of integration. There are oftentimes in integrating functions several different approaches to integrating a single expression, which might mean, even though that they are all valid approaches, that each approach will lead to a different way of expressing the final answer. They're all the same functional answer, but they might just be expressed in different formats. And this is something you should just be aware of. I believe I mentioned this earlier on. Sometimes you might integrate something one way, somebody else will integrate it a different way. You'll arrive at two expressions that look sort of different, but they are both correct antiderivatives. And it's just because there are a lot of ways of sort of converting between one expression to another, especially when working with trigonometric functions, because as you guys know, all of these secants can actually be thought about in terms of tangents, in terms of cosines, etc., etc. So just be very careful with that. All right, let's go ahead and summarize what we've seen so far and then talk about two very special situations. So, the summary for integrals of products of secants and tangents. It turns out that as we sort of talk about this, and we'll sort of go back to the examples we just did, we've handled almost all the cases. There is one case, though, that there is no general approach for, and we'll have to talk about that. So, if you have an indefinite integral of the form secant to the n tangent to the m of x, so a product of secants and tangents, then you can attempt the following here. If the exponent of secant, n in my notation here, is even, then what you should do is you should save a secant squared and convert the remaining secants into tangents using Pythagorean identity. Then you can use u substitution. So if the exponent of secant is even, you save the secant squared. If we go back, that was our first two examples. In this one here, we had tangent to the 5th secant squared, even power of secant. We saved the secant squared, didn't actually have to do any conversions, just immediately went to the u sub. Here we had secant to the 4th, that's a even power, saved a secant squared, converted the remaining secants into tangents, and u subbed. Okay? If the exponent of tangent is odd, then you can save a secant tangent and convert the remaining tangents into secants using Pythagorean identity. Then you can use u substitution. Those were the last two examples. Here we had secant to the 7th tangent. Notice that this was odd, so we did not save a secant squared. Instead, we noted that this was a 1 here. That's an odd power of tangent, so we saved a secant tangent. We didn't have to do any conversion, so we just immediately went to the u sub. Here, we actually, like we said, we could have done it both ways because the power was even for secant and the power was odd for tangent. We chose to go down the route of sort of focusing on the odd power of tangent. We pulled out a secant tangent, and then we converted the remaining tangents into secants, and then we were able to u sub. This situation basically tells us we know how to deal with even powers of secants and odd powers of tangent. The only thing it doesn't cover is in the sort of one opposite case, where you have an odd power of secant and an even power of tangent. Unfortunately, in that situation, an odd power of secant, even power of tangent, there is no general approach. Doesn't mean that you can't do them. There just isn't a general sort of strategy that applies to every situation. Instead, any situation like that, odd power of secant, even power of tangent, you're going to have to go through and sort of just try out different approaches. So this summary, along with the summary of sines and cosines, basically tells us how to deal with products of trigonometric functions. You might say, what happens if you have a product of sines and tangents, or of cosines and secants, or some combination? Well, if you have those, you should be able to use trigonometric identities to turn it into either a product of secants and tangents or a product of sines and cosines. So really, these two cases handle all products of trigonometric functions. For now, though, we're going to wrap up section 7.2 by looking at two very special integrals that actually fall into this category, where they have an odd power of secant and actually, in our case, no power of tangent, which is the power of 0, which isn't even. So we're going to talk about two examples of this. These two we're going to go through and derive together in this video, and then I would highly recommend sort of writing them down or memorizing them, because we're going to add them to sort of our table of antiderivatives. So in the future, we don't have to rederive these results. We can just immediately use them. So let's go ahead and talk about these. So the first sort of special case is just the direct integral of secant x dx. This certainly is a special one, because if we look back, it is an odd exponent of secant, the power of 1, and an even exponent of tangent, because it's a power of 0. So this has a sort of just very sort of simple trick. Some of you guys might have actually seen this integral in 190. If you haven't, we're going to sort of rederive it now. After we've rederived this, right, after we sort of do our work right here, then you guys will be able to just assume that you know what the integral of secant x is. You will just be able to use the result that we derive here. So the trick to doing this is actually to do an algebraic modification. That's a little complicated to start off with, but what we're going to do is we're going to multiply this expression by secant x plus tan x on top and bottom. Now, of course, because this is the exact same thing on top and bottom, that's not changing anything. This is the same as just multiplying by like 1 over 1 if we were to simplify that down, but it will help us sort of identify a technique here. Let's go ahead and distribute this secant up top. So we actually now have the integral of secant squared plus secant x tan x over secant x plus tan x dx. Now, could we try to simplify and cancel? Sure, but then of course we just get back to here. So we want to use this more complicated form. Why is this more complicated form good? Well, you should check out that top and sort of notice that it looks very suspicious. The top is secant squared plus secant x tan x. Literally, the top here is the derivative of the denominator. The derivative of secant is secant x plus secant x tan x, and the derivative of tangent is secant squared. So by this multiplication here, we've actually created the derivative of the denominator on top, meaning we can go straight into a u substitution. Let's let u equal secant x plus tan x. That means the derivative is secant x tan x, that's the derivative of secant, plus secant squared x dx. Notice that that is exactly what we have here. So we can go ahead and replace that. We get the integral. This is going to take out everything up top, so we're just going to be left with a 1 over. Down here, secant x plus tan x, that's what we're substituting, so we get 1 over u du. You guys now know how to integrate that. That's an easy one. That's just ln absolute value u plus c. And we pop the u back in there. So we get ln absolute value secant x plus tan x plus c. So now, if you guys hadn't seen this derivation already in your Calc 1 or your Math 190 class, now you've seen it. And now you know if you ever are just tasked with integrating secant x by itself, you now know how to do that. Anytime you see integral secant x, you can just immediately jump to this and you know how to integrate it. So this I would add to that sort of table of antiderivatives that we established at the very start of our class. In our sort of little 190 Calc 1 review, we made a big list of functions that we automatically know the antiderivative of. Now that we've done this for secant x, you should record that one in there as well. All right. In a sort of similar fashion, we're going to look at this example here, the integral of secant cubed. This is another sort of famous one because unfortunately, again, it falls into this category here. Power of secant is odd, power of tangent is non-existent, 0, which is even. So there's no general way to do it, but we have to just sort of come up with a manual sort of approach. We're just going to play around with it. Once again, once we finish this and come up with some sort of expression similar to this guy at the end, you guys should save that as a way of knowing that you now know the integral of secant cubed. The reason that it's sort of important to know the integral of secant cubed is it does show up sometimes, and it's nice to not have to rederive this result over and over again. So this is a really interesting one because, well, it just sort of involves playing around and noticing a nice little trick here. So what we're going to try to do is we're going to take this secant cube. We know that there's not much to do with it, but we could certainly break it up a little bit. Let's try to think about it as secant x, secant squared dx. Certainly we know we can do that. Now, we could try to mess around and take this secant squared and change it into 1 plus tangent squared, but then notice we don't have enough other secants to do a u substitution, so we probably don't want to try to do our Pythagorean identity. But this secant squared is still sort of convenient because we know that this is the derivative of tangent. And notice that the way we've written it here is a product. So we can try to do integration by parts, that technique that we introduced in 7.1. So let's try to do integration by parts and choose a u and dv with the idea that secant squared is very easy to integrate. So let's put secant squared x dx as the part that we're going to integrate, and let's differentiate the secant x. Now you might say, why don't we, integrate the secant x? I mean, technically we just did the integral of secant x up here, but think about this. I mean, this is a pretty nasty expression. I don't think we want to introduce this expression into an integral, because remember, after integration by parts, you still have another integral to do. Not a lot of hope to try to integrate this as a follow-up. So it's probably easier to integrate the thing that's very easy to integrate, secant squared. So our du here then would be secant x tan x dx, and our v, because we chose that secant squared, would just become tan x. All right, so according to integration by parts, we have that the integral of secant cubed dx is equal to uv, so secant x tan x, minus the integral of that v du. So it looks like if we multiply that out, v times du, looks like we would get secant x tan squared x dx. Okay, so notice that instead of having to do secant cubed, we now have to do secant x tan squared. Okay, let's go back and check. We've got odd secant even tangent, odd secant even tangent. Okay, so we're still stuck in this. It didn't make it any better where we jumped into one of these situations. Okay, so it's still not one that we can just easily u sub, but I guess we could mess around with it a little bit. I mean, we've got this tangent squared. We know a Pythagorean identity for that. There's not much else to do, so let's just put a Pythagorean identity in there. So secant cubed x dx is secant x tan x minus the integral secant x. And we know that tangent squared is actually equivalent to secant squared minus 1. So secant squared x minus 1 dx. And I guess we could multiply that out, and we get the integral of secant cubed x dx is secant x tan x minus the integral of secant cubed x minus secant x dx. Okay. Now this is a little bit better. I mean, we got two terms here, and we know how to integrate that term, the secant x, because, well, we just learned that up here. But this part, well, that's not exciting. That's a secant cubed, which is what we were trying to integrate in the beginning. So it seems like we're sort of stuck because we're back to where we began. But remember, we saw at the very end of when we discussed 7.1 a trick that if you can get back to the exact integrand you were originally trying to do, you can actually bring this over to the other side and solve algebraically. So that's what we're actually going to do here. We'll go on to a sort of second page here. Let's just grab what we've done so far and finish this thing up. Okay, let's copy that, give ourselves one more page to sort of do this on. Okay. Oops, I guess we brought along a miscellaneous integral sign there. Okay, there we go. So let's go ahead and distribute this negative sign. So we get the integral of secant cubed x dx is actually secant x tan x minus the integral of secant cubed x dx plus the integral of secant x dx. Okay, let's add this over to the other side. So we get 2 times the integral of secant cubed x dx is secant x tan x plus the integral of secant x dx. We just did the integral of secant x dx. It's back here. We know it's that ln structure. So let's go ahead and do that. 2 integral secant cubed x dx is secant x plus tan, or secant x times tan x, excuse me. Secant x times tan x plus ln secant x plus tan x in absolute value. All right, we divide by that 2. We get the integral secant cubed x dx is 1/2 secant x tan x plus 1/2 ln absolute value secant x plus tan x. And since we have finished our integral, there's our integral of secant cubed. We pop our plus c on at the end, and there we go. We actually managed to get the antiderivative of secant cubed. So there's 2 things I sort of want to briefly mention here. Notice that in the derivation of secant cubed, it relied on knowing the integral of secant x, which is why it's so important to have that one down in your table of integrals to know how to integrate secant x. So very important to be able to make this jump right here. And also, just as a technique, this is very, very unique. There are not many examples of integrals out there where you perform an integration by parts and then immediately get back the same integrand that we got here and then are able to solve algebraically. Like we said at the end of 7.1, we saw an example where you did 2 integration by parts, and because of the cyclic nature of the derivative of sine and cosine, you came back around to what you started on after 2 iterations. But on this one, we only did integration by parts once, and then we were able to get back to our original integrand and solve algebraically. So this is a very unique situation. You're not going to see that technique used too much. Last thing to sort of mention, because in section 7.3, which is our next section, we're going to be doing more of these trigonometric integrals because we'll be learning a technique called trigonometric substitution. Very important, to, along with that secant x sort of formula, to also have this secant cubed one down to just know that the antiderivative is this. You don't want to have to rederive this result that we took the time to do now. For now, though, this is going to wrap up section 7.2. In our next video, we'll be making our way into 7.3, which will be the integration technique known as trigonometric substitution.